And we developed this formula. The force of friction is equal to the coefficient of friction, which is mu, multiplied by what's called the normal force. In order for you to understand how to find a normal force in every situation moving forward, you have to draw the situation. Okay? And I know that most of you know the normal force in all of these problems is the force of gravity in magnitude and opposite direction. This is going to be especially important for the lab work you do today when we have an object that is on a horizontal surface. Whether it's moving horizontally or not, whether it's accelerating horizontally or not, the forces vertically are balanced. And if the forces vertically are balanced, and we know there's a force of gravity acting down on this object, then there has to be an equal but opposite force pushing the box or the object up. So if this is the force due to gravity, this is this force that balances gravity, and it's called the normal force. So calculating the normal force is an inaccessible calculation. There's no formula for it. But what you do is you look at this particular situation and you say that means the force of friction is equal to the coefficient of friction times the magnitude of the force of gravity, because these two vectors are equal but opposite. They have the same magnitude. And then you can say, well, I can calculate the magnitude of the force of gravity simply by taking mg. So this formula, if I ever asked you to show work in calculating a force of friction, and you started with that formula, that's incorrect. We've talked about this a little bit before with written response. If you use formulas that come from your formula sheet, you don't have to explain where they come from. This is not on the formula sheet. That means if you're going to use this formula in a lab or on a written response, you have to start with the one that's on your formula sheet, explain that you looked at this diagram, which turned this equation into that, which turned the equation into that. There's some physics going on here. This that I've got up here is physics. Putting numbers in is math. Really. It's using your calculator. So with all that being said, I just want to jump ahead and take a quick peek at question 8 and 9. Question 8 was missing an answer. I believe it's 0.51. And question 9 is missing an answer. I believe it's 0.12. Okay. So does anybody have any questions from any of these problems that you would like me to do? Go ahead. Right. And that's good because you're missing something in number 9. And there's a way to kind of cheat your way around it, but there's a way to do it properly. And what you're missing is the mass. So what we're going to do is talk about the hockey puck. Here's the edge. Here is the edge of the hockey puck. We're just looking at it on the ice. Starts moving with a velocity of 12 meters per second. Look, it isn't that somebody waves a wand and it's all of a sudden moving at that. It leaves the person's stick at 12 meters per second. And you know that even though ice is fairly low friction, if you've ever skated on ice or watched hockey, that puck is going to slow down. It doesn't just travel at 12 meters per second forever. There's friction slowing it down. And what you are told is it slows down over a period of 5 seconds. It's not a floating hockey puck. It slows down from this point, where it's moving at 12 meters per second, over here later on, it's moving at 6 meters per second. This is not drawn to scale. This distance is probably quite large. And it takes 5 seconds. To go from here to here is 5 seconds. So, this is a very important question, not because it deals with friction, but because of how we solve it. You are used to, so far, for the most part, solving problems where you have to use multiple equations. by using an equation to calculate something, taking that number, putting it into another equation and calculating something, and maybe continuing down that path. But this won't work. Because if we cut to the chase and it says, what is the coefficient of friction? Well, you would need to know the normal force. And you would need to know the force of friction. Well, the normal force is the force due to gravity in magnitude, but we don't know the mass. So on the one hand, we can't even find the normal force. The force of friction, and this next thing is important, but for a different reason. While this puck is moving, while it's moving from one location to another, it's moving to the right, but the force of friction is acting backwards. There is also, acting on this puck, a force of gravity and a normal force. Right? So this is the normal force. This is the force due to gravity. N here, when I write F sub n, is normal, not net. So I'm going to get back to the general point I was trying to make, and then I realized I have to make a different point first. This force of friction is the net force. And that's not just because a force is always a force. It's not because you look and you see newtons and you go, I'm going to throw it into this formula or that formula. It's the net force because when you, and I apologize for the tiny diagram here, but when you look at these three forces acting on the puck while it's in motion, those are the only three forces. So how do you add them? Well, you start adding the vertical, but the vertical is going to add to give 0 because the force normal is equal but opposite to the force due to gravity. So we also have this statement that F net equals MA, and I'm sure you're okay with me forgetting about the vector symbols here. Right? But the point I want to make is that the net force is the force of friction. They are the same force. I'm not saying they're equal but opposite. I'm saying the force of friction is the net force. There's a difference between saying that and saying they're equal but opposite. When I say two forces are equal but opposite, like, well, let me do this. I can write this statement, and this is true. This that I'm going to highlight is true. And the reason why I'm getting a little off track here, and I will get back to the question in a minute, is we just had this conversation less than an hour ago in Physics 30 about magnetic forces. It's an important idea. This is a true statement, okay? My question to you is this a true statement? It's not. Those two forces are not equal. They're equal but opposite. This is false. This well, I'll ask you, is this true? Now it's true. So I'm going through an awful lot here, but again, I teach Physics 30, so I know what's important. The point I made in my Physics 30 class this morning, and it wasn't frictional forces, it was magnetic forces, is that these two forces up here, highlighted in blue, these two forces are equal because they are the same force. There's only one force. It's the force of friction. And I can call it the force of friction, or I can call it the net force. But it's just one force described in two different ways. These two forces in yellow have magnitudes that are equal because the forces are actually equal but opposite. There's a big difference. Okay, now getting back to the question, let's refocus here. On the one hand, we have this equation which relates the force of friction to the coefficient of friction, which we're after. On the other hand, we have the net force, which equates the net force to the mass and the acceleration, and we know that these two things are equal. So, in the past, what you have been taught to do, because it's all your brains can cope with at earlier levels, with a lot of people, is you say, well, if I want to find the coefficient of friction, I need to find the force of friction. The force of friction is the net force, so I'm going to calculate the net force. But no matter what you do, you can't find anything. Because to find the force of friction, you would need the normal force, which is related to the mass, and we don't know the mass. To find the net force, you would need to know the mass. So we solve this in a different way. We solve it by starting here. Now, I hope you agree that if those two forces are equal, I'm looking at the blue in case you're watching this on video, if the highlighted blue forces are equal, then this is also true. Would you agree that's still true? Okay. Well, that means that MA, which is how we calculate net force, equals mu Fn, which is how we calculate force of friction, but the normal force is the force due to gravity. Looking at the vector diagram, this normal force is not accessible to calculate, but we know looking at it that it's equal to the amount of gravity. So rather than writing MA equals mu Fn, we can write MA equals mu Fg. This is what I mean when I say we build a formula. How do you calculate mg? Well, on your formula sheet, it's... how do you calculate the force due to gravity? Well, on your formula sheet, it's mg. I don't know if many of you noticed, but I said mg earlier, because when I see force of gravity, I automatically think mg. So in this case, the mass times the acceleration has to equal mu times the mass times g, but we can mathematically cancel the masses. And what I would say to you, and it's almost hinging on our conversation yesterday after class, Alex, is you could kind of cheat your way out of this by making up a mass. By saying, I'm going to say the mass of the hockey puck is 200 grams. What you will discover is to find the net force, you'll multiply by that made-up mass, but then over here someplace to find mu, you're going to end up dividing by that made-up mass. But that's not the best way to do it. The best and proper way to do it is everything that I have here. And boy, there's a lot going on, right? Now what happens, Ashlyn, is we can cancel the masses. And if we want to find mu is equal to the acceleration over 9.81. And we're going to have to use kinematics here to find the acceleration. By the way, the acceleration is in a negative direction of the motion, but we really don't care about that. Let me do the calculation and explain what I mean by that, in case it's lost on some of you. Acceleration is Vf minus Vi over t. So if we take 6 meters per second minus 12 meters per second and divide by the time of 5 seconds, you actually get a negative acceleration. I think it's 1.2, by the way, is it? Yeah. But what I'm saying is when we go over here, we never use vectors with forces of friction. We never use positives or negatives. Well, I shouldn't say never. Never is a bad word. But in this particular case, the coefficient of friction is just going to be the amount of acceleration over 9.81. So now we can finish the question and put 1.2 meters per second squared divided by 9.81 meters per second squared. This equals the coefficient of friction that we're after, and that's going to be about 0.12, which is what I said the answer was. Any other questions? Oh. I'll clean that up later. Just move your books out of the way. Sorry about that. All right, we're going to be doing a lab today. I have a handout for you to kind of guide you. The first lab we did in the semester, I talked about lab reports because many of you are going to go to post-secondary where you have to do lab reports. The emphasis here, though, is on content, not on the exact structure of the lab report. So the handout is going to guide you through what it is I would like you to do. And this handout is due, I'm going to say Wednesday of next week. So that's not the day we return from your long weekend, but the second day back. You should have no problem collecting your data in time today. The thing that's going to be different about this lab is the type of analysis we do, which is called a graphical analysis, which is something you need to know how to do on the diploma exam next year. And again, I teach Physics 30, so I kind of know what's around the corner for all of you. You're welcome. What that is. I have not had a chance to obviously take a look at your work from the last lab activity, but remember what I told you. I'm expecting a level of quality here for your work that you turn in that's quite high. I don't want scribbles. I don't want a graph. You're going to be doing a graph here as part of your analysis. I don't want a graph that looks like it was completed by a small animal recovering from surgery and just waking up in a daze. I want it nice. Okay? All right. So what are we doing today? We're doing a lab today. That involves friction. And the purpose, there's kind of two purposes to this activity. The first purpose is to show that the coefficient of friction between, that should say two materials. I was a little rushed this morning and typed it up. And I guess I didn't proofread it well enough. One of the purposes is to show that the coefficient of friction between two different materials is constant. What do I mean by that first statement? Well, what I mean is that if I take an object, and the object you're going to be using is a block of wood. If I take an object and I put it on the floor, I'm going to use a counter or a tabletop in demonstrating this because I don't feel like crawling around on the floor. You guys can do that later. If I say to you that I want to determine the coefficient of friction between this desk and this wood, and I say it's constant, what I mean is it doesn't matter whether it's moving fast or slow. It doesn't matter how much material is on it. It's this material of wood on this material of laminate on the desk. It shouldn't matter. The coefficient of friction is going to be the same no matter what. Okay? The other thing we want to do is actually determine what the coefficient of friction is. Okay, so that's maybe the bigger part of the lab. And I'm not going to write down the answers to any of your work here, but I'm going to explain what I would expect, so you might want to jot down a few things. Not on this sheet of paper, because that's what you're going to be turning in. You might want to have, someplace else where you can jot a few notes. By the way, I would like you to add something to this handout. There are two types of coefficients of friction, or two types of friction. One is static and one is kinetic. We're talking here about a kinetic force of friction and calculating the kinetic coefficient of friction. That means the coefficient of friction while the objects are in motion, or while the object is moving. So, how are you going to do this lab? The setup is so simple. You require just a few items. One of them is some weights. One of them is a block of wood with a hook on it. And one of them is a spring scale. Now we're dealing with horizontal surfaces here. And by the way, each group will have two sets of these weights, and I will tell you why in a second. Your setup is to hook your spring scale to the wood, and that's it. You're going to do measurements based on this. You're going to be measuring a force, and it's important that when you pull on the object, you don't pull at an angle. You pull so the spring scale is horizontal. And for that reason, what you'll want to do to begin with is lay your spring scale down on the horizontal surface. And I want you using the floor. The desks and the counters are too slippery for this. I want more friction. The reason why you want to lay it horizontally is so that you can make sure it's zeroed. We talked about this the other day. That mark or that piece of metal that sticks out on the scale has a thickness to it. And you need to, with your partner, decide, am I going to go with the top of that, with the bottom of that, with the middle of that? But, in throwing all of these in a drawer, what might have happened is this metal piece, that one's really glued in tight, doesn't move. But a lot of these metal pieces move, so you might need to readjust it to zero it. Okay? So that's the setup. You're sitting there, you've got your spring scale attached, you've got your wood. By the way, on all of the pieces of wood, someplace it tells you the mass of the wood. So we don't have to worry about finding any masses here. They're given to you. So this one, if you have this piece of wood, it's 514.6 grams, which is 0.5146 kilograms. So you set up the lab as instructed by Mr. Way. So you're sitting there. I want you using the floor, so this stuff is all on the floor. And what you're going to do is you're going to measure the magnitude of the applied force needed to move the mass horizontally at a constant speed. Okay. How do you know it's at a constant speed? Well, if it's speeding up, then the force has to be quite large. And if it's slowing down, the force has to be small. So if I dragged this block of wood across the floor and I sped it up and let it slow down, I would discover that the reading on the spring scale wobbles back and forth. It increases, it decreases. You want to be moving that over a fairly big distance. I'd say at least a meter, just to be sure. Doesn't have to be, but I'm just saying a meter would be sure. And you want the force over that distance not to be increasing or decreasing. And if you're pulling it over, say, half a meter or a meter, and the whole time the force is 3.5 newtons, then that's the applied force needed to move it at a constant speed. Okay? And what you're going to do is change the total mass and measure what the new force would be. So I have, I'll use this one. I have this, and I do it. I'm just going to say that it's, I don't have my good glasses on. I'm going to say it's, I want to just check my scale. 1.4, 1.3 newtons. By the way, you need to be aware of this. When you're measuring anything with a mechanical device, things that have small values will have a greater error in your measurement. Because if my error in this measurement is like 0.25 newtons, and I'm measuring 1.3, that 0.25 newtons is a pretty big chunk of 1.3. But if I'm measuring a force that's this big, that error is not as significant. So I would have 1.3 newtons. And what I would record, if you turn to the next page on your handout, is in the table, and I didn't copy the table up here, but what I would record, your first column says F applied in newtons. So your first column, I would record 1.3 newtons, and the second column says mass, and I would record 0.5146 kilograms. 0.5146 kilograms. And the magic number that I choose whenever I talk about high school labs is 8. I think if you can get 8 data points, that's preferred. I don't think you can here. Some of you might have an extra weight that we can use to find an 8th data point. But your data points are going to be, this is my recommendation, you're going to have 2 sets of masses. And what you don't want to do, if this is 514 grams, you don't want to then take, can you read what that says stamped on there? 20. You don't want to go, I'm going to go 514 grams, and then I'm going to add 20 grams to it, and I'm going to repeat the experiment. You want to space out the masses so that when you're adding more mass, it becomes significant. And my recommendation is 500 grams. This is your first data point, whatever it is. 628.3 grams. This block of wood is 514.6. My next one is going to be 500 grams more. So what I'm going to do is here I'm going to have 1.0146 kilograms, which is 514.6 kilograms plus 500 grams. So these are going up by 0.5 kilograms each time. And I will repeat the experiment, and I will measure the new force. I'm not going to do that. Then you can do a kilogram. So you can take the 500-gram one off and add a kilogram one. And now we're at 1.5146. And then you can add another 500 grams. I think this is 500. Does that say 500?
I think so.
Yeah. And then you can add another 500. Well, so what are we at here? This is 1, 2, 3, 4, 5. Now we're at 2 extra kilograms. 6. Actually, we can do 7. You can probably do another, yeah, I think you can. 200, 200. 100. You can do 8. You can do, let me just outline this for you. The block, and then the block plus half, the block plus 1, the block plus 1.5, the block plus 2, the block plus 2.5, the block plus 3, and the block plus 3.5. Is that 8? 1, 2, 3, 4, 5, 6, 7. That's 8. I think you can get 3.5 kilograms on here because each of these are a kilogram. These are 500 each, so that's another kilogram. So we've added 3, and you should be able to get another 500 grams out of the remaining pieces. You're still with me? Okay, so you're going to collect your data. You're going to collect 8 sets of data. Then what you're going to do, and I'm going to kind of not rush, but move through the rest of this fairly quickly, you're going to calculate the force due to gravity for all of the masses. So in your table, you've entered 0.5146 kilograms. The next column is the force due to gravity. Of course, you multiply by 9.81, and you're going to get about 5 point something newtons. Just a rough estimate in my head. You're going to do that for all 8 sets of data. Still with me? Okay. Then you have to explain why the applied force that you've entered is the force of friction. I'm not going to answer that for you. But basically on your chart, may I? On your chart, you have this column that says applied force, and the second last column says force of friction. You can copy all of these applied forces into the force of friction column. This question is asking for a good explanation as to why we're allowed to do that. Five says, explain why the normal force, which we didn't measure, is equal to the amount of gravitational force. So in your data table, the middle column, you filled in all of the weights or the force due to gravities. The final column says normal force. You're going to copy all of your force due to gravities into the normal force, but you need to explain why you were allowed to do that. The reason why we do all of this is the last 2 columns are normal force and force of friction, and those are the things in the formula that has mu in it. Force of gravity is not in there. Applied force is not in there. Then you are going to make a graph. And you're going to graph this, 6. I'm missing number 7, which says make a graph. So on your handout, there's a graph. And it says complete a graph of the force of friction as a function of, I know I have this someplace because I fixed it, as a function of, I've lost it. It should say as a function of the normal force, not the force of gravity. This is pretty important. And again, I just typed this up this morning. No excuses, but I didn't catch this until after I printed it. As a magnitude of the normal force, as a function of the magnitude of the normal force. So your last 2 columns are going to be what you use for a graph. When you say force of friction as a function of, that means force of friction goes on the vertical axis. I better pick up the pace. I want to give you guys enough time to get your data. So you need to construct, for number 7, you need to construct this graph. Force of friction, normal force. And I want you scaling things so that you use a lot of the graph paper. Don't make a really awkward scale, but when you look at your graph, horizontally, there are 9 big squares horizontally. Would you agree? I would say that if your normal forces have a biggest normal force of 4 newtons, you should probably go, there's a square here, you should probably go 1 newton, square 2 newtons, square 3 newtons. I mean, don't make some weird scale like each square is 1.95 newton. Don't do that, because then it's hard to locate those data points. But that way, that will take you to most of the horizontal width of the graph. If you count the squares going up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are 12 squares going up. Let's say that your biggest force of friction is 2 newtons. No, it'll be more than that. Let's say that your biggest force of friction is 12 newtons. Well, then you'd go 1 newton for each square. If your biggest force of friction was 20 newtons, then you'd have to scale that back a bit. All I am getting at here is I've given you this graph that's this big. We'll wait for it to come up. I've given you a graph that is a fair size. I don't want you using just a little corner of it. Whatever you construct needs to use most of the space. My general rule is at least half. Now take a look while we're waiting for my computer to catch its breath. Wow, it's not even a rectangle. Let's take a look now at 3 and 4. How is the result, how is your graph going to show you that the coefficient of friction is constant? And I'll give you a hint. Your graph is force of friction as a function of normal force, and the force of friction is supposed to be equal to the coefficient of friction times the normal force. What should your graph look like if the coefficient of friction is the same all the time?
Like a straight angle.
Straight angle. Now, it may, in theory, it should go through the origin. It may not, because maybe your spring scale is measuring everything a little bit higher. So, in theory, the graph should do that, but maybe it looks like this. Okay. Anyway, you're going to have 8 data points, and I would recommend when you plot the data points, you plot a point and you circle it. I guarantee you, I don't think they're going to fall in a perfect line, but they're not going to do this. They're not going to do this. They're going to be in a fairly straight line. So when you draw your line of best fit, which is what that's called, you put your ruler down where you think it represents the data. To get into a set of rules as to exactly where you place it requires university statistics. Okay, we don't want to go there. You use your best judgment. So I would answer this question by saying, well, since the coefficient of friction multiplied by the normal force gives you the force of friction, and we get a straight line showing a proportionality, then the coefficient of friction is constant. But this is the part that I want you to carry over into Physics 30. If this graph looks like that, and let's imagine it goes through the origin even though yours may not, the equation of this line from math is y equals mx. Would you all agree? Okay. What's m in this equation? Slope. Well, this is y. This is x. What is that? What conclusion do you draw from that? That the slope is equal to the coefficient of friction. We're not going to calculate the coefficient of friction 8 times. We're going to find the slope of this line and determine the coefficient of friction by explaining this, that by comparison, the slope has to be the coefficient of friction. And when you find your slope, by the way, to finish your activity, you're going to have a whole bunch of these data points, right? 8 of them. When you find your slope, you want to pick 2 points on the line that are reasonably far apart. You don't want to use these 2 points to find a slope. And you want to pick points that you can read accurately. Then you can find your rise and your run. Take your rise divided by your run. After you've explained what I've highlighted, you're done. It's a straight line, so the coefficient of friction is constant. Add the slope of the line as the coefficient of friction, because I've explained it, which is 0.35. By the way, I know what the coefficient of friction is between wood and the floor. Part of your mark is based on your results. That explanation went a little bit longer than I wanted it to, but I think you have a half hour, a little bit more. That is enough time to collect your data. Okay? You just have to be organized. There are blocks of wood at the back of the room. You're going to need 2 sets of weights. Some of the weights have the hook that's been broken off, which means it says 500 grams, but it's probably 495 or 498. Don't worry about it. Spring scales are at the back. Let's get going.